What if the biggest threat to artificial intelligence isn't a shortage of chips, not regulation, not a lack of data, not even the possibility that AI development slows down? What if the real problem is something far more basic: electricity? Right now, the world's biggest technology companies are spending hundreds of billions of dollars building the infrastructure needed for the artificial intelligence revolution. Bigger data centers, more advanced chips, massive clusters of GPUs, entire campuses filled with computers powerful enough to train models that would have seemed impossible just a few years ago. But behind all of this sits one uncomfortable reality. Every AI chip needs power. Every server needs power. Every cooling system needs power. And the more powerful artificial intelligence becomes, the more electricity it consumes. This is quickly turning into one of the biggest hidden problems in the technology industry, because the AI race may be moving faster than the infrastructure supporting it. And some of the most powerful people in technology appear to understand exactly what's coming. Jensen Huang, Sam Altman, Elon Musk, and many of the world's largest technology companies are making enormous infrastructure bets. But here's where the story gets strange. Some tech leaders are no longer thinking only about building AI infrastructure on Earth. They're looking up toward space. And if their predictions are correct, the next major phase of the artificial intelligence revolution could completely reshape the global energy industry, the power grid, and perhaps even the space economy. To understand why, we first need to understand just how much computing power artificial intelligence actually requires. For decades, computing became more efficient. Computers became smaller, processors became faster, and the cost of computing gradually declined. But artificial intelligence has created a completely different type of demand. Modern AI models require enormous clusters of specialized chips working together. We're not talking about a few computers sitting inside an office. We're talking about warehouses, massive buildings filled with servers, thousands upon thousands of advanced processors operating almost continuously. These facilities are known as data centers, and data centers have existed for decades. Every Google search, every Netflix stream, every cloud file, every Instagram post, all of these services rely on data centers somewhere in the world. But AI is changing the equation. Traditional internet services mostly respond to simple digital requests: load a web page, retrieve a file, play a video. AI models perform enormous numbers of mathematical calculations. When you type a question into an AI chatbot, somewhere inside a data center, powerful processors begin running calculations to generate a response. One question doesn't sound like much, but multiply that by hundreds of millions of users. Then add image generation, video generation, AI coding, scientific models, autonomous vehicles, robotics, and AI agents potentially operating 24 hours a day. Suddenly, the amount of computing infrastructure required becomes enormous. And that's before we even talk about training. Training a modern artificial intelligence model requires huge clusters of GPUs running for extended periods. The industry is now building models with more data, more compute, and increasingly complex architectures. This creates a simple relationship. More powerful AI requires more computing. More computing requires more chips. More chips require more data centers. And more data centers require more electricity. That's the chain, and electricity may be the weakest link. Jensen Huang, the CEO of Nvidia, has become one of the most important figures in the AI boom. Nvidia's GPUs are at the center of modern artificial intelligence infrastructure. The company's chips power many of the world's most advanced AI systems. And Huang has repeatedly emphasized that the AI revolution will require an enormous infrastructure build-out. We're talking about investment measured not in millions, not even billions, but potentially trillions of dollars across the broader industry. Think about what that means. The internet revolution required telecommunications infrastructure, fiber optic cables, cell towers, servers, undersea cables. The automobile revolution required roads, highways, gas stations, factories. Artificial intelligence may require its own infrastructure revolution, except this infrastructure consumes an extraordinary amount of power, and companies are already making massive commitments. Projects involving tens of gigawatts of potential computing capacity are being discussed. To put that into perspective, a gigawatt is an enormous amount of electricity. 1 gigawatt can represent the output of a large power plant. Now imagine multiple gigawatts dedicated primarily to computers, machines running AI calculations, and the ambitions continue to grow. Sam Altman, the CEO of OpenAI, has spoken extensively about the relationship between artificial intelligence and energy, and one of his comments reveals the scale of the problem. He described a future where society may face difficult choices about how energy is allocated. Imagine a country has a limited amount of electricity. That electricity can power homes, hospitals, schools, factories, transportation systems, or enormous AI training clusters. Now imagine AI companies requesting more and more power. At some point, policymakers may have to ask a very uncomfortable question. How much electricity should be dedicated to artificial intelligence? Because power grids were not designed for this. Most national electricity systems were built gradually over decades. Power plants are constructed based on expected demand. Transmission lines carry electricity across regions. Local grids distribute that electricity to homes and businesses. It's a complicated balancing system. Electricity demand and electricity supply must constantly be managed. managed. Then suddenly, a technology company arrives and says, "We want to build a massive data center, and we need enough electricity to power a small city." That's not a normal customer. A house might use a few kilowatts. A small business might use significantly more. But hyperscale data centers can demand hundreds of megawatts, and future AI campuses could potentially require gigawatts. This creates a problem. You can't simply plug a massive AI facility into the grid and hope everything works. New transmission infrastructure may be required. New substations, new generation capacity, new cooling systems, new backup systems, and all of this takes time. Building an AI model can happen relatively quickly. Building a power plant cannot. Constructing major electricity infrastructure can take years, sometimes more than a decade when permitting, regulation, environmental reviews, and political opposition are involved. And this creates a massive mismatch. AI development is moving at software speed. Energy infrastructure moves at construction speed. One industry measures progress in months, the other measures progress in years, and that gap is becoming increasingly important. But the problem isn't only technical, it's becoming political. Across the United States, local communities are beginning to question the rapid expansion of data centers. At first, a massive technology investment sounds attractive. A major company arrives. It buys land. It promises investment. Local officials announce a huge project. The headlines sound incredible. Billions of dollars flowing into the region. But then residents begin asking questions. How much electricity will this facility consume? How much water will it use? How many permanent jobs will it actually create? And most importantly, who is going to pay for the infrastructure upgrades? This is where the situation becomes controversial. Electricity grids require enormous investments. If utilities need to expand generation or transmission capacity to support data center demand, those costs have to be financed somehow. And local residents fear that part of the burden could eventually appear on their electricity bills. Imagine opening your monthly power bill. It's higher than last year, then higher again. Meanwhile, a giant data center nearby is consuming an enormous amount of electricity. Even if the economic relationship is complicated, the political narrative becomes extremely simple. My electricity bill is going up. The AI data center is consuming massive amounts of power. Therefore, the data center is the problem. That's how political opposition begins. And we're already seeing examples of this backlash. In Franklin Township, a proposed Google-related data center project became the center of a major local controversy. The project represented exactly the type of infrastructure investment technology companies need for the AI era. But local opposition grew. Residents raised concerns. Political pressure increased. And eventually, the project failed to move forward as planned. Now think about what this means for the technology industry. The problem is no longer simply finding land or buying GPUs. Companies need something much more difficult: social permission, political permission, grid access, energy contracts, and communities willing to host massive computing infrastructure. Data centers are slowly becoming politically radioactive in some areas. Not everywhere, but enough that technology companies have to pay attention. Because AI companies are racing against each other. OpenAI wants more computing power. Google wants more computing power. Meta wants more computing power. Microsoft wants more computing power. Amazon wants more computing power. Every major player is trying to secure chips, data centers, and electricity. If one company faces a 3-year delay because of local opposition, that's not just a construction problem. It could become a competitive problem. In the AI race, 3 years is an eternity. Think about where artificial intelligence was 3 years ago. Now imagine where it could be 3 years from today. A delayed data center could mean delayed models, delayed products, delayed revenue, and potentially losing ground to competitors. This is why electricity is becoming a strategic asset. For decades, technology companies primarily competed for software engineers. Then they competed for cloud customers. Then AI companies began competing for GPUs. But the next competition may be for megawatts. Companies are already looking for regions with available power, places with cheaper electricity, faster permitting, more supportive governments, and stronger infrastructure. This could reshape where the world's AI infrastructure is built. The United States currently sits at the center of the artificial intelligence revolution. Many of the world's most important AI companies are American. Many leading chip designers are American. The largest cloud companies are American. But AI infrastructure doesn't necessarily need to stay in America. Computing can move. Data centers can be constructed in other countries. If electricity is cheaper in another region, if permits are approved faster, if governments actively support massive AI campuses, then companies have an incentive to look outside the United States. The Middle East, for example, has shown growing interest in artificial intelligence infrastructure. Countries with enormous energy resources understand that AI could become one of the most important industries of the century. Historically, energy-rich countries exported oil and gas. But what if the future involves exporting computing power? Instead of shipping barrels of oil around the world, a country could use its energy domestically to power massive AI data centers. The energy becomes compute, and compute becomes a global digital product. This could completely change the economics of energy. Regions with abundant power may suddenly gain a major strategic advantage. Nuclear power is also returning to the conversation. For years, nuclear energy faced political resistance in many countries. High construction costs, long development development timelines, safety concerns. But AI is creating enormous demand for reliable, continuous electricity. Solar power is useful. Wind power is useful. But data centers operate 24 hours a day. AI doesn't stop working when the sun goes down. And large computing clusters need stable electricity. Nuclear energy can provide large amounts of continuous power. This is why technology companies are becoming increasingly interested in nuclear projects. Some are exploring advanced reactors. Others are supporting existing nuclear facilities. The connection between technology and energy is becoming stronger. In the future, an AI company's competitive advantage may partly depend on its energy strategy. Who has access to the cheapest electricity? Who can secure the most reliable power? Who can build data centers fastest? Who can negotiate the best agreements with utilities? These questions sound like questions for an industrial company, not a software company. But that's exactly the point. AI is transforming technology companies into infrastructure companies. The biggest AI players are no longer just writing code. They're building physical systems, chips, servers, cooling facilities, power infrastructure, transmission connections, massive industrial campuses. Silicon Valley is colliding with the energy industry. And this brings us to one of the strangest possibilities in this entire story: space. For decades, the idea of building large-scale computing infrastructure in space sounded like science fiction. Launching hardware into orbit is expensive. Repairing equipment is difficult. Communication creates challenges. Radiation can damage electronics. There are thousands of technical problems. But Elon Musk and other technology leaders have started discussing the possibility of space-based computing. And when you look at the electricity problem on Earth, you begin to understand why. On Earth, a data center needs electricity. That electricity has to come from somewhere. A power plant, a solar farm, a wind farm, a nuclear reactor. Then electricity must travel through infrastructure, transmission lines, substations, local grid connections. The data center also generates enormous amounts of heat. Computers get hot. GPUs operating at high intensity generate significant heat. If that heat isn't removed, the hardware cannot operate effectively. So data centers require sophisticated cooling systems. Cooling requires additional energy. In some designs, it can also require significant water resources. Now consider space. In orbit, solar panels can potentially receive sunlight more consistently depending on the orbital design. There are no clouds, no weather systems blocking sunlight, no local community complaining about a giant industrial facility being built next door, and heat management operates under completely different physical conditions. Now, space cooling is not magically easy. In fact, removing heat in a vacuum is a serious engineering challenge because there is no air to carry heat away. Spacecraft rely on radiation and specialized thermal systems, but proponents believe future orbital computing systems could be specifically engineered around these conditions. Then there's scale. Earth has limited land, limited grid capacity, political boundaries, environmental regulations, local governments, community opposition. Space has a completely different set of limitations. Theoretically, enormous computing infrastructure could eventually be placed in orbit, powered by large solar arrays, connected through advanced satellite communication networks. Imagine thousands of computing satellites, not simply transmitting internet signals, actually processing artificial intelligence workloads, a giant distributed computer surrounding the planet. It sounds absurd, but remember something important. Many technologies sound absurd before the economics make sense. Reusable rockets once sounded unrealistic to many people. Private companies operating massive satellite networks sounded unrealistic. Landing rocket boosters vertically on autonomous ships sounded like science fiction. Then SpaceX did it. The key question isn't whether orbital AI data centers are easy. They're not. The question is whether the problems on Earth become expensive enough that space starts looking attractive. That's a completely different calculation. Imagine building a data center on Earth costs $10 billion. Then grid upgrades are required. Permitting takes years. Local communities oppose the project. Electricity prices increase. Environmental lawsuits begin. Construction gets delayed. Suddenly, the true cost isn't $10 billion anymore. It's the money plus the delays. And for an AI company, delays can be incredibly expensive. Now imagine launch costs continue declining. Rockets become more reusable. Satellite manufacturing becomes cheaper. Robotic systems become more advanced. AI itself helps design and operate orbital infrastructure. The economics slowly begin to change. Space-based computing doesn't need to become cheaper than today's data centers. It needs to compete with tomorrow's increasingly constrained data centers. That's the important distinction. And Elon Musk may be uniquely positioned for this possibility. Think about the companies connected to Musk. SpaceX operates rockets. Starlink operates a massive satellite network. xAI is developing artificial intelligence systems. Tesla has experience with energy storage and large-scale computing. These capabilities overlap in a very interesting way. Rockets can launch hardware. Satellites can provide communication. AI companies need computing infrastructure. Energy systems help manage power. Individually, these businesses operate in different industries. Together, they form pieces of a potential space computing ecosystem. This doesn't mean Musk will definitely build giant AI data centers in orbit, but the strategic possibility is difficult to ignore. And Musk isn't the only person thinking about the relationship between space and computing. The broader broader space industry is changing rapidly. For most of human history, space was controlled almost entirely by governments. NASA, the Soviet space program, national space agencies. Projects cost billions. Launches were rare. Hardware was custom-built. But commercialization is changing the industry. Private companies are reducing launch costs. Satellite production is becoming more standardized. Entire satellite constellations are being deployed. The infrastructure required for a space economy is slowly being constructed. AI could accelerate that development because AI has something previous space projects often lacked: enormous economic demand for computing. The Apollo program was driven by geopolitical competition. Satellite networks were driven by communications. But AI infrastructure could potentially create another reason to expand into space: energy and computing. If AI demand continues growing exponentially, companies will search for every possible source of computing capacity. Earth first, then perhaps orbit, and potentially, much further into the future, the moon. The moon receives enormous solar energy. Certain locations near the lunar poles may have extended periods of sunlight. There are proposals for lunar infrastructure, mining, energy production, scientific bases. Now imagine computing facilities eventually becoming part of that infrastructure. Again, this is extremely long-term, but investors should understand how major technology shifts develop. The biggest opportunities often look ridiculous in the beginning. In the 1990s, buying products through a computer seemed strange. Then Amazon became one of the world's largest companies. Social networks initially looked like websites for college students. Then they became global communication platforms. Cryptocurrency started as an experiment discussed in obscure internet forums. AI chatbots were once simple programs that barely understood language. Now artificial intelligence is influencing hundreds of billions of dollars in corporate investment. The future rarely arrives looking obvious. It usually arrives looking impractical, then expensive, then interesting, then inevitable. But before investors start buying every company with the word space in its presentation, we need to be careful. There is a major difference between a technological trend and a good investment. The dot-com boom proved this. The internet was absolutely revolutionary. The optimists were correct. The internet did change the world, but many internet companies still went bankrupt. A correct prediction about technology does not automatically create a profitable investment. The same applies to AI infrastructure and space infrastructure. Hundreds of companies may attempt to enter these industries. Many will fail. Some will run out of money. Some will have interesting technology but no profitable business model. Some stocks will become wildly overvalued. Investors need to identify where actual economic bottlenecks exist. And right now, one of the clearest bottlenecks is power. Think about the AI supply chain. At the top, you have AI applications, chatbots, coding tools, image generators, video generators, enterprise AI systems. These applications rely on AI models. The models rely on computing infrastructure. Computing infrastructure relies on GPUs and specialized chips. Those chips operate inside data centers, and data centers rely on electricity. Electricity is the foundation underneath the entire stack. Without power, the most advanced GPU in the world is just an expensive piece of silicon. This is why investors should watch the power industry carefully. Utilities were once considered boring investments. Slow growth, predictable demand, regular infrastructure spending. But AI could change electricity demand in certain regions. If massive data centers are constructed, utilities may need to expand: new power generation, new transmission systems, new substations, new grid technology. This creates opportunities, but it also creates risks. Utilities operate in heavily regulated environments. Large infrastructure projects require capital. Debt levels matter. Interest rates matter. Regulators determine how costs can be passed to customers. Not every utility will benefit equally. The key is location. Where are AI data centers being built? Which utilities serve those regions? How much spare grid capacity exists? What energy sources are available? How quickly can infrastructure expand? These questions may become increasingly important for investors. Then there are energy companies. Natural gas could play a role because gas power plants can provide reliable electricity. Nuclear companies could benefit from renewed interest in continuous, carbon-conscious power. Renewable energy companies may find enormous new customers in technology. Energy storage companies could become increasingly important. And then there's the physical grid itself. Transformers, high-voltage equipment, transmission infrastructure, electrical components. These aren't exciting AI chatbots. They don't generate viral demos, but they're essential. During a gold rush, sometimes the most reliable business isn't searching for gold. It's selling the equipment. AI may create a modern version of that idea. Everyone is focused on the model companies. Which AI model is smartest? Which chatbot has the most users? Which company releases the next breakthrough? Meanwhile, the companies building the physical infrastructure may quietly benefit from the entire industry's expansion. But there's another risk investors should monitor: hyperscaler migration. Hyperscalers are companies operating enormous cloud computing infrastructure. Microsoft, Amazon, Google, Meta, in its own massive infrastructure ecosystem. These companies invest billions of dollars in data centers. Historically, the United States has been an attractive place for this infrastructure. Strong technology ecosystem, access to capital, large customer base, political stability. But electricity constraints could change investment investment decisions. Imagine one country offers cheap power, fast permits, tax incentives, available land, and government support. Another country has expensive electricity, 5-year permitting delays, community opposition, and uncertain regulation. Where do you build the next $10 billion data center? Capital moves toward efficiency. AI infrastructure may gradually move toward regions where energy is abundant. This could create new technology hubs, not because those regions have the best software engineers, but because they have the best electricity. That's a major shift. For decades, technology geography was shaped by talent. Silicon Valley became powerful because engineers, entrepreneurs, and investors concentrated in one location. But AI data centers don't need thousands of software engineers sitting next to them. A model can be developed in California and trained on infrastructure located thousands of miles away. The physical compute can exist wherever the economics make sense. That means the geography of AI infrastructure could look very different from the geography of AI companies. The headquarters might be in San Francisco, the engineers might be in California, but the data center could be in Texas, or Virginia, or the Middle East, or Northern Europe, and eventually, perhaps, orbit. This creates an interesting investment framework. Instead of asking only, which AI company will win, ask a different question. What does every AI company need? Every major AI company needs chips. That's why Nvidia became so important. But every chip needs electricity. Every data center needs cooling. Every facility needs grid connections. Every expansion needs construction. Every large project needs financing. The AI boom is much larger than software. It's becoming one of the biggest industrial buildouts of the modern era. And industrial buildouts create second-order opportunities. Think about railroads. The railroad boom wasn't only about railroad companies. It increased demand for steel, coal, land, construction, financial services. Entire cities developed around transportation networks. The automobile industry didn't only create car companies. It created oil giants, tire companies, highway construction, insurance companies, parking infrastructure, fast food restaurants designed around drivers. Technology creates ecosystems. AI will do the same. We're currently focused on the most visible layer, chatbots. But underneath the chatbot is an enormous physical machine, and that machine is getting bigger. The question is whether our infrastructure can keep up, because if it can't, the AI industry may face a wall. Not a technological wall, an electrical wall. You could design the most powerful artificial intelligence model ever created. You could have the best researchers, the best algorithms, the best data, but if you can't secure the computing capacity required to train it, the model remains theoretical. This is why the next phase of the AI race may look less like Silicon Valley and more like an energy competition. Companies negotiating power agreements, investing in nuclear projects, building private generation capacity, searching for regions with available megawatts, potentially designing data centers around dedicated power plants. We may even see AI campuses become more vertically integrated. Today, a technology company buys electricity from the grid. Tomorrow, major AI companies could effectively control their own energy infrastructure. Imagine an AI data center built next to a dedicated nuclear reactor. Or a massive solar facility combined with energy storage, or natural gas generation specifically constructed for computing. The line between technology company and energy company begins to blur. And this could create political tension, because electricity is not an ordinary commodity. It's essential infrastructure. People need electricity to live modern lives. Hospitals need electricity. Factories need electricity. Schools need electricity. Governments cannot simply allow unlimited AI demand to destabilize the grid. If electricity prices rise dramatically, voters will react. If blackouts occur, politicians will react. If data centers are blamed, regulation will follow. This is the difficult choice Sam Altman was pointing toward. How much computing is enough? If training a more advanced AI model requires enormous amounts of energy, society may eventually ask whether the benefits justify the cost. AI companies will argue that more advanced models could transform medicine, science, education, productivity, economic growth, and they may be correct. But policymakers will still face trade-offs. A megawatt used in one place cannot simultaneously be used somewhere else, unless new generation capacity is built. That's why energy expansion is so critical. The AI industry doesn't simply need to consume more electricity. It needs the world to produce more electricity. A lot more. This could be one of the defining investment themes of the next decade. The artificial intelligence revolution may indirectly trigger an energy revolution. Nuclear power could accelerate. Grid modernization could accelerate. Renewable construction could accelerate. Energy storage could accelerate. Space infrastructure could accelerate. Not because society suddenly became obsessed with electricity, but because intelligence itself is becoming an industrial product. Think about that. For the first time in history, companies are building machines capable of generating something that resembles digital intelligence at enormous scale, and manufacturing that intelligence requires energy. In the Industrial Revolution, energy-powered physical machines, steam engines, factories, trains. In the AI revolution, energy powers cognitive machines, models that write, analyze, design, code, generate images, control robots, and perhaps eventually perform millions of tasks currently done by humans. If AI becomes deeply integrated into the global economy, electricity demand may become become connected to digital labor. More AI agents working means more computing. More computing means more power. The world's future workforce could partly exist inside data centers, and those digital workers need electricity. This is why the power bottleneck matters so much. It's not simply a temporary problem. It could be a structural feature of the AI economy. Efficiency will improve. Chips will become more powerful. Models may become more efficient. Software optimization will reduce waste. But history shows that efficiency doesn't always reduce total consumption. Sometimes it increases it. When something becomes cheaper and more efficient, people use more of it. Computers became more efficient. We didn't use fewer computers. We put computers everywhere. Internet bandwidth improved. We didn't consume less data. We started streaming 4K video. AI models may become dramatically more efficient. But if billions of AI agents begin operating continuously, total computing demand could still explode. This is known as a rebound effect. Efficiency lowers the cost. Lower costs increase usage. Increased usage drives total demand higher. That's the scenario technology companies appear to be preparing for. A world where AI is everywhere. Inside businesses, phones, cars, robots, factories, hospitals, schools, scientific laboratories. And behind all of these systems sits infrastructure, the invisible foundation of artificial intelligence. So what should investors actually watch? First, watch hyperscaler spending. Microsoft, Amazon, Google, Meta, and other major technology companies regularly report capital expenditures. These numbers reveal how aggressively companies are building infrastructure. If spending continues increasing, the AI infrastructure boom remains strong. But listen carefully to management commentary. Are executives mentioning power constraints, grid connections, permitting delays, data center availability, energy costs? These details could reveal where the bottlenecks are developing. Second, watch geography. Where are new AI data centers being announced? Which states? Which countries? Which regions? If major projects increasingly move outside traditional technology markets, ask why. The answer may be electricity. Third, watch utilities. Not every utility. Look at the regions experiencing rapid data center growth. Study electricity demand forecasts. Look at capital spending plans, transmission investments, generation projects, but also watch regulatory risk. If residential electricity prices rise, political pressure could increase. Fourth, watch nuclear energy. Technology companies need reliable power. Nuclear energy provides continuous generation. Small modular reactors and advanced nuclear technologies are receiving growing attention. The industry still faces enormous challenges: cost, regulation, construction timelines. But AI demand could create powerful customers willing to support development. Fifth, watch the electrical equipment supply chain. Transformers, switchgear, power management systems, cooling technology, data center construction. These are the physical components required to turn electricity into computing. And finally, watch space carefully. Space computing remains speculative. The technical challenges are enormous. The economics are uncertain. Most companies discussing futuristic space infrastructure may never build profitable businesses. But don't ignore the direction of travel. Launch costs are declining. Satellite networks are expanding. AI demand is growing. Earth-based infrastructure is facing constraints. When multiple trends move toward the same point, investors should pay attention. The most important thing is not predicting the exact year when AI data centers move into orbit. Maybe it happens sooner than expected. Maybe it takes decades. Maybe another technology solves the power problem first. The important thing is understanding why serious technology leaders are even considering these ideas. Because it reveals the scale of the infrastructure problem. The AI industry is searching for power, massive amounts of power, and the search may reshape industries far beyond technology. Energy, utilities, construction, nuclear power, natural gas, renewables, electrical equipment, and space. The biggest winners of the AI revolution may not all have AI in their company names. Some may be companies that simply provide the electricity, the cooling, the grid equipment, the land, or the infrastructure required to keep millions of GPUs running. During every major technological revolution, attention focuses on the visible product. During the internet boom, people focused on websites. During the smartphone revolution, people focused on apps. Today, we're focused on AI models. But behind every revolution is infrastructure, and eventually, infrastructure becomes the bottleneck. Right now, the world is racing to build artificial intelligence faster than perhaps any major technology in modern history. Companies are investing hundreds of billions of dollars. Governments are treating AI as a strategic priority. Engineers are building increasingly powerful models, but all of that intelligence depends on something incredibly simple: a steady flow of electrons. No electricity, no GPUs, no data centers, no AI revolution. And that's why the next great battle in artificial intelligence may not happen inside a research laboratory. It may happen at power plants, at utility commissions, inside local government meetings, across transmission networks, and perhaps, one day, hundreds of miles above the Earth. The AI race started with algorithms. Then it became a race for chips. Now, it's becoming a race for energy. And the companies that understand that shift early may be the ones that control the infrastructure of the future. Because artificial intelligence may be digital, but the resources powering it are very, very physical. And as AI grows, the world may soon discover that the most valuable valuable resource in the technology industry isn't data. It isn't chips. It isn't even intelligence. It's power.